Hello everyone, my name is Bao. I'm a PhD student from the University of Adelaide, Australia. I'm very honored to share my work titled Februus, Input Purification Defense Against Trojan Attacks on Deep Neural Network Systems. Today, deep neural networks have surpassed human performance and are trusted in critical applications such as self-driving car or cancer detection. However, in 2017, deep neural networks were shown to be vulnerable to Trojan attacks. In a Trojan attack, an adversary embeds a backdoor to gain privileged access and control the decision of the network. This backdoor can be activated by any input with a secret trigger known only by attackers to hijack the system for malicious purposes. For example, in this traffic sign recognition task, placing the secret trigger on any traffic sign will activate the backdoor to cause all inputs to be classified to the class targeted by the attacker, in this case the 100 km/h speed limit. Such an attack can lead to catastrophic accidents. Why are Trojan attacks a threat? Build a deep neural network model requires a huge amount of costly label training data, computational power, and expertise to train. Consequently, people are outsourcing that training to an entrusted third party in a so-called machine learning as a service paradigm, or taking advantage of transfer learning by using free, potentially untrusted open-source pre-trained models from model zoos. Hence, the supply chain of deep neural network can now be exploited by attackers to inject Trojan into the network. This attack method is very powerful because attackers can freely choose the secret trigger and targeted label. Our motivation is that Trojan attacks are powerful and easy to deploy. However, methods for defending against Trojan attacks are lacking, and these attacks can cause catastrophic consequences if deployed in critical applications. And in 2019, recognizing this threat, the U.S. Army Research Office solicited techniques for defending against Trojans in AI systems. And detecting Trojan attack is challenging because Trojan trigger is inconspicuous to human beings. And Trojan trigger can be any shape, size, and pattern freely chosen by attackers, making it impossible to guess. And deep neural networks with millions of parameters are not human readable, making it hard to detect whether the network is Trojan. And the more important metric users care about is model accuracy, and that is the big point because Trojan DNA has an identical accuracy with the benign model for benign inputs, except when the trigger appears. The research community has developed a number of defense methods. Fine-tuning neuroclean did inspect focus broadly along the lines of cleaning and restoring the performance of the Trojan network, while Sentinel and Street focus on detecting a Trojan network at runtime, whereas ABS focus an offline method for detecting a Trojan network. We explore a new defense concept. We ask the question, can we apply the classic notion of input sanitization that is widely used in software security systems to defend against Trojan attacks? This concept can be particularly useful in applications where detection is not enough or denying the service is not an option. For example, in this traffic sign recognition task, can a potentially Trojan DNA still correctly identify the stop sign even in the presence of the secret trigger? In our work, we consider a realistic threat model where the adversary trainer wants to manipulate the DNA to misclassify all inputs with the Trojan trigger to a specific targeted class, what we call input agnostic attack. He or she has full control on training and poisoning process, meaning whiteboard setting, and the attacker can wrap the Trojan trigger with any shape, size, and pattern. As a defenders, we have no access to the information of the Trojan trigger or poisoning process, and the defenders have a herald clean dataset to verify the defense method. We observe that there is a bias in the Trojan DNA. We can see there are similarities between distribution of deeply learned features between the benign model and the Trojan model for benign inputs, explaining the identical accuracy from both models. However, when a trigger appears, any input to the Trojan is misclassified to a horse, the targeted class. Now the distribution of deeply learned features so that the Trojaning process created a bias in the network. Let's shift on inputs with the chosen to a universal representation. We observe that bias leaks its information, and by exploiting a visual explanation tool such as breadcrumb, we are able to reduce the bias. Essentially, the secret Trojan trigger accounting for the bias is exposed because the salient feature of the Trojan is the most important factor in the network decision in an input agnostic attack. Subsequently, we propose to surgically remove the influential region because the secret trigger is the key to activate the backdoor. One naive approach is to mask the trigger, but it will lead to a degradation of classification performance by at least 10%. So how can we maintain the performance of a DNN while neglecting the effect of the Trojan? We propose to restore the input through image restoration to recover the original likeliness of the image. Inspired from recent work in image imprinting, we propose our image restoration based on generative adversarial networks or GANs to reconstruct the surgically removed region once occluded by the chosen trigger. This is attractive because unlabeled data can now be used to build the defense method. We build a generator to restore the removed regions. In order to generate a higher fidelity reconstructed region, instead of using one discriminator as in a traditional GAN, we incorporate two different discriminators, a global and a local one, into a Wasserstein GAN. This approach helps improve the realism of the reconstructed region as well as stabilize the training of GAN. These two lots will be fed back to the generator and added together with the mean square error loss to improve the fidelity of the restored images. Our image restoration method helps to recover the performance of Trojan DNA. We combine the idea of removal and image restoration to propose the Februus system for input sanitization. When the Trojan input appears, Februus still process and make a correct prediction. With our system, it will be misclassified to a split limit. Februus remove the Trojan trigger at runtime, and we will show that Februus, while focusing on input agnostic attacks, is also a robust defense against advanced and adaptive attacks. We attempted to create realistic, complex, and physically deployable triggers in real-world scenarios. We did the experiments on three different visual applications, which are scene, face, and traffic sign recognition. Here's the results. This is the baseline accuracy of the benign model, and the Trojan model has similar performance. After adding Februus system, the network performance was still maintained, while the attack success rate dropped significantly from 100% to mostly 0%. So we have successfully defended against input agnostic attacks. Here are some examples of Trojan inputs with the secret trigger under Februus. Those secrets would be exposed and sanitized to defend against a Trojan attack. Februus also showed the robustness against advanced backdoor and adaptive attack, and we are the first to quantitatively analyze and provide the defense against the strong backdoor of the partial Trojan. We also implemented some robust adaptive attacks to testify the robustness of Februus. The first one is attack targeting Trojan removal, where attackers try to add adversarial perturbation noise to the inputs to mislead the breadcrumb happening at the inference time. Although this is our trace model for a Trojan attack, where attackers use realistic natural trigger, we observe that adding large magnitude adversarial noise while potentially mislead the breadcrumb, having the adverse effect of neglecting the Trojans, hence reduce the attack success rate. Another adaptive attack is to target the image restoration module. Attacker can increase the trigger size, hence causing the difficulty for Februus to restore the inputs. Although Februus still can block the attack, the classification accuracy after Februus degraded to 80% when the trigger covers 25% of the image. However, a large trigger makes the Trojan attack not inconspicuous anymore. Or the attacker can create multiple pitch triggers to cause the difficulty for our GAN-based image restoration to restore multiple regions. However, with no assumption on the size set and location of the trigger during the design of our image restoration, our Februus is highly generalizable and can restore multiple regions as shown in the figure. Attackers can also try to embed the breadcrumb knowledge during poisoning the network. However, due to the contradictory objectives between concealing the salient of the trigger features and achieving state-of-the-art result, increasing the breadcrumb knowledge during the poisoning process will degrade the classification accuracy while leading the network to neglect the effect of the Trojan. As a non-line method, we also evaluate the runtime overhead of Februus. In the worst-case scenario, the runtime overhead is around 30 milliseconds, and our results are comparable with Script and much faster than Sentinel. Notably, these methods are only detection. Here are our contributions. We propose a new defense concept where we can exploit the Trojan introduced bias leak in the network to localize and surgically remove the trigger in inputs and restore the inputs using image inventing to achieve highly accurate model performance even in the presence of the Trojan inputs. And our method is tailored for time-bound systems where the detection of the Trojan and discarding an input is not an option. Februus is plug-and-play, compatible with pre-existing DNS systems in deployments and operate at runtime. Our method is robust defense against input-agnostic Trojan, as well as advanced backdoor and adaptive attack. Februus can reduce the attack success rate in the worst case to under 0.25% across 3 classification tasks, and all of the shortcut is released as the link. We have tested our method on vision domain, but the concept of input sanitization can be further developed on other domains such as text and audio, which will be left for future work. Thank you for your attention.